I know. I'm like, what the hell is she? Wait, let me see. Am I? Okay.
Can you mute yourselves, please? Good morning, everyone. I'm just giving another minute or so because I still see students are joining and we have the waiting room on. So I just have to admit all in the meantime. We have a student as iPhone guest. Usually we want students coming as registered students. I'm not sure, so I haven't admitted that person. If you know them, can you please let them know if they could just come as Toro student? I'm not sure who this is. All right. I think we can get started now. We have most of the students, and this is getting recorded. So you will get the recording as well.
Recording in progress.
Once we have it ready. All right. Good morning. How's your morning been today? All good?
Been good.
Pretty good.
All right.
Thank you.
All right,
So far,
let's
so
see.
good.
What are you saying?
Oh, I'm having a great morning so far.
Very nice. All right, happy to hear that. And let's get started where we had left off yesterday. There were a few questions that I want you to prepare. So anyone who can answer this question, we are not running a poll, but and it's not graded either. So if you're ready, please raise your hand and then we can go from there. As I told you before, this is the type of questions that you will be seeing in the exam. Yes, Marcia, please go ahead.
Good morning, good morning.
Good
This
morning.
one I got 12, and what I did was I took the patient's body weight, converted it to kilograms, and then I multiply it times the total body water, which is 60%. And then from there you have to also convert it to the ECF. So I did 1/3, and then I multiplied it again against 3/4 because it's specifically looking for a section in the ECF. So that's how I got there.
Great, thank you.
Yes, ma'am.
Is everyone clear about this? What are we doing here? Did you do the homework yesterday? Can I ask someone who has done it, the homework? Can anyone tell me if they have done the homework? Can they tell me their total body water? Not that I'm picking on anyone's weight, but yes, Andrew, please go ahead.
Oh, yes, thank you, doctor. Yeah, I just did it, and yeah, I have my total body water weight is 54 liters of water.
54 liters, very nice. All right, so what will be your interstitial fluid then?
Oh, it would be 13.5 liters of water.
Is everyone getting the point what we are discussing? You have the calculations right up here. I would suggest go 60, 40, 20 rule. 60% of your body water approximately, right? And then 40, 20 rule. I know the girls will probably ask like 55%. Yes, go accordingly. And then do 40% of that and 20% of that. And then out of 20%, you want to make sure that 15% is your interstitial fluid and 5% is plasma. And more you try to do such questions, challenge yourself, do a couple of times for plasma, for ICF, and I think you will be fine for the exam. Yes, everyone is with me? All right, let's move to the next question then. Is everyone clear about the examples that we had discussed yesterday? So again, the question comes up, if we are blocking the primary active transport here, how would you kill the secondary active transport? Anyone? If you got the point, then please explain. How do you think? Yes, Noah, please go ahead.
Because the gradient is destroyed, that's powering the secondary active to come through. So it doesn't use ATP, but it requires on the concentration gradient.
Beautiful. So just keep in mind, if you don't have sodium gradient as steep as needed for the symport of glucose or antiport that or any other function that it helps with, you are not able to bring these molecules in, right? Or ions in or out. So for healthy secondary active transport, you have to have your primary active transport active as well, right? So if it is killed by any means, then we have some issue, right? Any other examples for primary active transport? Do you remember the pumps that we discussed yesterday? Yes, Andrew, go ahead.
Oh, yes, thank you, doctor. Well, we have the hydrogen potassium pump in the stomach, which basically pumps acid into the lumen of the stomach, and then basically allows potassium to go into the circulation.
And any other example? I can take another volunteer here. We discussed another one yesterday. Yes, Marcus, go ahead.
The calcium ATP pump.
Calcium ATPase pump, very nice. What does it do?
It pumps calcium against its gradient into the cell by hydrolyzing ATP.
Very nice. Yes. So just remember that calcium has to be more outside, right? So the gradient has to be maintained all the time. So that's what your calcium ATPase pump, which is sitting on the plasma membrane, will be doing. It's going to push calcium out using that calcium pump. We call it PMCA. It is different from CIRCA. Anyone who can explain CIRCA. So we have two calcium ATPases working in your cell. There is one PMCA and there is one CIRCA. Now, anyone who can explain us the difference between the two and the function. Anyone else besides Andrew? All right, Andrew, go ahead.
Oh, thank you. So the circus stands for the sarcoplasmic reticulum one, and that's basically in our muscle fiber. So to help basically with moving of the muscle, basically you'll have like the dihydrogen and ryanodine receptors. The calcium basically spills out of those and basically activates the pulling of the muscle fibers.
Yes. So what does CIRCA do again? What does CIRCA do? Yes, Noha?
It holds in the calcium gradient.
Yes, yeah. So basically, again, it is acting against the gradient, right? So it is the calcium that has been spilled into the muscle fiber to get the excitation contraction coupling going. When the muscle contraction has ended, the calcium has to be accumulated back into the sarcoplasmic reticulum so muscle can relax. Otherwise, if your muscle is under constant contracted condition, muscle is gonna, get tired and give up, right? So it's best to give it relaxation between the excitation contraction coupling, right? So once the contraction has been completed, the calcium will be gathered inside into the sarcoplasmic reticulum, and that's what CIRCA do, right? It's going to collect all that calcium and put it back into the sarcoplasmic reticulum, and that's what your calcium ATPase pump is doing. It's working against the gradient. You have more calcium sitting, and it's going to gather calcium from the muscle fiber and bring it back into the sarcoplasmic reticulum, and it will be stored there until we have the next excitation contraction coupling coming. We will finish this whole mechanism once we get into MSK. So yeah, just don't feel that you don't know the mechanism. We will go over like point by point, how does CIRCA work and how does your muscle relax. So once we get there, you will know it, but at this moment, you should definitely be knowing our active transports that are going on in the cell. So just remember the examples that I have given you already. Okay, did everyone go over this table yesterday? Okay, I don't see very many videos on. It's just, if more videos are on, then I can see that everyone is actively listening. So can you tell me what is the potassium concentration inside the cell? Any volunteer for that?
It's 120.
Yes, absolutely. Thank you, Zara. So as you can see here up on the table, and I told you at least your sodium and potassium numbers should be imprinted in your minds. And it will help you throughout learning physiology, whether we are doing cardio, pulm, GI, renal, especially renal. I mean, these numbers, everywhere they will be helpful, but for now, just remember it, okay? So you can see that sodium is your ECF cation and potassium is your ICF cation, yes? And you can also see calcium is more outside, chloride is more outside, bicarb is more outside, so these are the holding numbers. And they will be maintained all the time. Now, again, the question comes back. I asked you yesterday, I'm just revisiting those topics again. why do you think that these concentration differences, they are maintained? And which are the active mechanisms that are maintaining these concentration gradients? Why do you need them? We are just revisiting the topics. Yes, Thomas?
It's maintained by the sodium potassium ATPase and the negatively charged proteins that exist in the plasma that can't leak through the capillary wall help to keep a negative charge that pulls out some of the positive charge of the cations.
Beautiful, very nice. So not only sodium potassium ATPase, which is basically maintaining your sodium and potassium numbers, but calcium ATPase also plays a big role here. Those are the active mechanisms they'll be maintaining. And of course, there will be some exchanges that are going on with for chloride and bicarb that we will be learning time to time as moving forward. But for now, I mean, the active transport, passive transport, secondary active transport, those are the points that we should be knowing for this exam. So that's why I'm paying more attention to those. Thank you, Thomas. All right, so now question comes back. We talked about cardiac glycosides yesterday. This is a drug that is given for cardiac arrhythmias or congestive heart failure. I mean, this is not primary drug of choice, so just keep that in mind. We are just, I think it's a great source of learning when we are learning the transports. So let's say if we are giving cardiac glycoside to a patient, which is basically aborting the function of sodium potassium ATPase pump, what do you think is going to happen? And how does it help the patient? Jacob?
So it's going to block the sodium potassium pump, and therefore it's going to cause less depolarization of the cell, and so it's going to slow down that arrhythmia.
Very nice. That is one function. What else is happening? You said it there, but you were one step ahead. Can you tell us the in between stuff that has happened? So if you blocked this, right? You just said it. You block this. Yes, medicine?
You're going to increase the intercellular sodium, and then the K plus concentration will decrease.
Beautiful. Thank you. Yes. So we meant to say that first of all, you are killing the sodium gradient outside, right? And you are retaining more sodium inside of the cell. That is correct. Is everyone getting my point? Yes. Olivia, you had something to add? You can go ahead.
Oh, I was gonna ask a question about you had mentioned yesterday in lecture that this is also how you can control blood pressure in patients for like hypernatremia. So I was
Say it
gonna ask,
again. Say it again, Olivia.
I was just gonna ask about how this would affect blood pressure because you had mentioned that the sodium going in different directions, like hypernatremia, and then you can block it with that. Is that kind of the same?
I mean, those are little bit non-related things, but if you are blocking the pump, obviously you are retaining more sodium inside, and that is definitely gonna uh, take an impact on the sodium concentration outside. So that's for sure. But for now, our goal is to determine how do you help this patient with cardiac glycosides. And Jacob mentioned some things which are absolutely correct, but you got to tell me what else you are accomplishing by using to stop the pump, using the drug stopping the pump. Anyone else? Yes, Murad. Murad, go ahead. You are on mute. You are on mute, Murad.
Can you hear me now?
Yes. Mhm.
Yes. So maybe a stronger heart concentration, contraction.
Very nice. How? That's what.
By causing the calcium to build up inside the cell.
Calcium to go inside the cell? You are there, but I mean, you don't have the exact mechanism. I'm just trying to get to the point so you can tell me what we are trying to achieve here by using this drug. Marcia?
Yeah, I'll try to help him. So when you inhibit the sodium potassium pump, what happens is you also decrease the ATP being used, and then you can also block the calcium and sodium, which will have calcium staying on the inside, which will accumulate, which will cause the heart to contract even more because you have more calcium being stored in.
Very nice. Thank you. So what are we trying to achieve here? We block the pump, right? So we kill the gradient. Now there is more sodium that is retained inside, right? So cell will have more sodium. Now, if your concentration gradient is killed outside, you have lesser of a drive that was taking sodium in, right? Now your calcium sodium exchange is going to get impacted as well, which was the antiport mechanism that we were talking, right? This is our secondary active transport that will be killed. So you have in the muscle fiber, you'll have more sodium retained as well as more calcium retained, right? Now, if you have in cardiomyofibers more calcium retained, it will definitely impact the contraction and you'll have a forceful contraction that will help the patient against arrhythmias and set the rhythm pattern. Is it clear to everyone? Murad, is it making sense now? Murad, did you get the point? Okay, is everyone with us on this? Is it clear enough? Yeah, it's going to come back when we are doing cardio again. And multiple times, actually, you will see this example pop up. Yeah, I see something in chat. Yes, Deborah is already put in the chat. Thank you, Deborah. Are we all good? Like, if you are killing the primary active transport, how would you impact secondary active transport? So this is a great example for that. As I told you, this is not a drug of primary choice anymore these days, but it's a great example to learn how do we block the primary active transport and then further ruin the secondary active transport from there. Okay. Okay, one more question coming your way. Let's say we put an inhibitor to SERCA. SERCA is your calcium ATPase pump sitting on your SR, right? That was accumulating calcium from the muscle fiber and bringing it into the SR. If you put an inhibitor to that, what do you think will happen to the muscle fiber? If you put an inhibitor, yes, Jonathan. Go ahead.
Yeah, so the calcium's going to linger in the muscle cell and it's going to keep contracting.
Beautiful. Thank you. So you are not able to accumulate that calcium, bring it back into the SR. Your calcium is staying in the muscle fiber for a longer time, so muscle will be under repeated contractions. Very nice. Yeah, these are the, tricky mechanisms that if you think a little bit, out of the box, you are able to get those mechanisms. Are we all good on this? Remember, there will be questions for primary and secondary active transport or other modes that we have discussed so far. So just be ready for the exam. All right. Okay. And GLUT2 is doing what kind of transport here? GLUT2? Anyone? This is just a revisit from yesterday. GLUT2 is what kind of diffusion? Yes, Catherine.
Sorry, I forgot to press unmute. GLUT2 is taking glucose out of the cell.
Yeah, so we call this as
Facilitated.
facilitated diffusion. Yes, Amelia, thank you.
Amelia.
All right, I think we are good. Now we are moving on to the renal portion or the fluid shifts that we were discussing yesterday. We couldn't touch it yesterday. This is actually when we used to have supplemental sessions in person. We used to do these things as whiteboard exercises, but I'll try to help you out as much as we can via Zoom. But if more help needed, just let me know. We can figure it out next week again. All right. So let's go one by one and just raise your hands. Don't say anything, and we'll go from there. Okay, so if I am going by hypertonic and hypovolemic, which box you think matches that? Stephen has his hand up. Yes, Stephen, please go ahead. Hypertonic and hypovolemic, and you will have to explain as well from the board. From the box, sorry. Oh, we can't hear you, Stephen. You were on unmute, but somehow we couldn't hear you. Do you have earplugs on? We can't hear you still. Sorry. You can put
Can you hear me
chat.
now?
Yes, absolutely. Go ahead.
Okay. You can hear me now?
Yes. Thank you. Go ahead.
Okay, cool. Sorry. The hypertonic solution would be outside on the upper on your y-axis. So, and your hypovolemic would be retained within the x-axis as liters. So we're looking at probably for hypertonic and hypovolemic, we're looking at B, the box of B.
Beautiful. Thank you. So what Stephen is mentioning, in case for others who still haven't understood the whole box diagram situations, here is the solid box, which is representing a normal patient, where sideways you are looking at the volume, and if you go up, you are looking at what are you looking at? Anyone? Yes, Larry, go ahead.
Osmolarity.
Osmolarity, right? So in a patient, if there is a change in osmolarity or in the volume, blood volume or plasma volume or the cellular volume, we are talking about hypovolemia or hypervolemia. So hypovolemia is this dotted contraction that you see away from the solid line, right? If you see this dotted line going up, that means there is an increase in the osmolarity upwards, right? So if there is a contraction, the dotted line will go inside the box. If there is an expansion, the dotted line will come out. So patient will be retaining more volume, the dotted lines will come out of the box, right? So this is what we are discussing here. Hypertonic and hypovolemic goes to B. Thank you. Now, next one, hypotonic and hypervolemic. Next volunteer. Yes, Madison, go ahead.
That would match with figure D.
Hypotonic and hypervolemic.
Yes. Can you hear me?
Yes. Thank you, Madison.
Oh, sorry.
So I was just giving everyone a chance to look at that. Hypotonic, you see this space here. So the solid line is up here and the dotted line is coming down. So patient is hypotonic and they are hypervolemic because they have expanded out of the box. The dotted lines, they are both. The cells are swollen and even their plasma volume or ECF volume is more, right? So patient has definitely retained more water or more volume inside their body. And that's how their osmolarity has gone down. Now, next one is hypotonia and ECF hypovolemia. Yes, Letty, go ahead.
That one would be C, and I have a question afterwards though, but we see
Yeah,
the
sure.
hypovolemic bulimia.
So what is it? Hypotonia and
Mhm.
ECF hypovolemia.
So it should be C.
It should be C. Very nice. C is matching C. You can see that it's hypotonia, it's down, right? And then ECF, hypovolemia. So ECF is hypovolemic, whereas ICF, so the water is shifted towards the cells. Cells are swollen at this point, and ECF is gone down from the volume perspective. Now your question.
Would it ever be described as ICF hypervolemia, or no? We'd only stick with ECF when answering the question.
So I'll tell you from the next slide on, like how the shifts are going to happen, but you will see it very clearly what we are asking.
Thank
Okay?
you.
Yeah, it will be very clear cut what we are asking you. And as long as you have done what the examples that we have given in Costanzo or what I'm discussing here in supplemental, that should be good enough for the exam. Okay? As long as you know the shifts. And I will always say, if we are giving you certain clinical scenario, you got to draw it out. Don't just, memorize the concept. You will have to draw them out and see the shifts, how they are happening. I'm going to explain actually from next slide on. We will try to work on it, okay? Not leaving you alone with this, because the scenarios will be real, the clinical, and you will have to draw them out. All right, next one, D is isotonic and hypovolemic. Volunteer for this. Yes, Catherine, please go ahead.
Would it be A?
That's going to be A. Now, can you explain us why did we say isotonic and hypovolemic?
Because the dotted line is within the boundaries of normal, but there is less on the right, which it corresponds to the x-axis, which means that it's less volume. Hence isotonic, because the y-axis is the same as the regular box, and hypovolemic because it's shorter than on the x-axis.
Beautiful. So basically it's hypovolemic in the ECF, but osmolarity is similar as it is coinciding with the solid box, right? So there is no change in osmolarity and there is a volume depletion here. Now let's go back and Catherine, thank you actually, very nicely you explained. Now which situation, if you go to the clinical scenario, what do you think will represent this condition? Yes, Andrew, go ahead.
Oh, for this case, it would be something like a hemorrhage or bleeding, where basically you're bleeding out like plasma fluid.
Yes. Yeah. So someone who's bleeding, they're losing their plasma, right? It's ECF, volume contraction, because if there is no osmolarity change, then you will just see the ECF contraction, right? If you're losing from the plasma, you didn't enter any sodium into the body or you didn't take much sodium out of the body, as long as those conditions were not there, you're only gonna see a depletion in the ECF. Okay, and Andrew is absolutely right. That would be a hemorrhage, would be the clinical condition that will go with it. Yes, Noah?
Would the ICF eventually become hypotonic if the ECF is becoming hypertonic? Or
Yes. I mean, whenever you are introducing more salt, I'm going to get there in the next slide. So listen here. So your normal osmolarity is 290 milliosmoles, right? And in a steady state, body tries to be having same osmolarity in the ICF or ECF, like keeping it similar. And that's where when we are talking about sodium playing a role in your ECF chambers and potassium playing a role in your ICF chambers, how body tries to maintain those numbers all the time, right? But since sodium is a major ion that takes role in your osmolarity. So there are three things that you are looking into when you are looking for the osmolarity is your glucose, sodium levels, and your BUN, blood urea nitrogen. These three things, they make your osmolarity. And usually the number stays near about 290. Okay? So as long as you didn't introduce more sodium into the body, someone like who's really fond of eating chips, too much salt you introduced into the body, it's gonna change your osmolarity in the ECF, right? And moment you introduce more sodium, the first chamber where sodium is getting introduced into is going to be your ECF. Remember that. And we already discussed that sodium is your ECF cation, right? So if there is more sodium getting introduced, it's going to bring your osmolarity up, right? The moment osmolarity is going up, what's going to happen? If you are introducing, so question is, if introducing more sodium into the ECF chamber, what will happen next? Yes, Shelly.
The water moves into the high osmolarity space.
Water will
move into
exactly. So there is a golden rule, wherever there is more sodium, water will follow. So your cells will try shrink and send some water towards the ECF in order to maintain the same osmolarity in both chambers. That is what is going to happen. Your cells will shrink and they will try to send more water here. So it's going to compensate for that more sodium that is entering here. So everything is at the same osmolarity eventually. Is everyone getting my point or no? I see there is something. Yeah, okay. All right. Are we all good or no? If you have questions, you can ask me now. Or you can see me personally if you still think, you have questions, you can see me personally if you're not getting the points. All right. So I just told you if you're entering more sodium, there will be water shift that's going to take place. Or if there is any scenario where sodium is getting out of the ECF, you don't have enough sodium in the ECF, what will happen then? So if I give you a condition where you don't have enough sodium in ECF, what will happen? Yes, Letty, go ahead.
The ICF will also shift too, right? It'll shift the water from the ECF into the ICF.
Yes. So now if you have less sodium here in this chamber, then it's gonna less sodium, yeah. And this one is low osmolarity. Water will shift towards the higher osmolarity. So the cells will be swelling now. Is everyone clear? Yes? All right, let's do this question. When you are ready, raise your hand. So we are looking for a condition out of A, B, C, D. Which one do you think is representing diarrhea here? Yes, Thomas, go ahead.
It's A.
A is the right answer. Very nice. Thank you. So how do you say that? You got to explain us.
Sorry. So he is losing fluid, but he's not losing salts, so it's not going to suck the osmolarity or change the osmolarity. So we'll have decreased fluid in the extracellular, but it won't change anything else.
Okay, I'm just gonna make a correction to your answer here. Oh, Sabrina is answering something. Yes, Sabrina?
Can you hear me?
Yes, it's coming with echo, but we can hear you, but there is an echo.
Oh,
Yeah, it's okay. Let me explain it. So what Thomas mentioned, that there is fluid loss that this patient is experiencing when they are having bouts of diarrhea, right? Just remember, if they're losing as much solute with this water contraction that is happening in this patient, they have to lose isotonic fluid from here for us to see ECF, isotonic volume contraction. Is it making sense to everyone? They lost as much solute as they did water from the. Remember, whenever someone is having a hemorrhage or they are having diarrhea, they are basically losing volume out of the plasma, right? Plasma will be the first one, and that's how you see blood pressure going down right away, right? So ECF, if blood loss is happening, in case of hemorrhage, you will see again isotonic contraction in ECF volume, right? Isotonic because osmolarity is not changing. Solute is also going down along with the water that they are losing, right? Same thing in diarrhea. If they are having bouts of diarrhea, they are losing volume, but they are also losing solute as well. That's why we don't see any change in osmolarity, but we see their plasma going down, and we're going to see ECF volume contraction. Is it clear to everyone? Are we good? All right, great. I'm not discussing other options because we have them in the next question coming up. Okay, I won't discuss everything here, but this is a great, great questions here up on screen. So let's go match one, number one. What do you think is happening in number one? What do you match it with? You can think, take your time, don't rush. Yes, Jonathan, go ahead.
I believe it would be B, drinking 1 liter of pure water would increase the ECF.
Not really, Jonathan. That won't be right, and I will explain in a minute why that won't be right. Stephen, do you want to take it?
Hopefully you guys can hear me.
Yes.
It's going to be the infusion. It's going to be D, the infusion of the isotonic saline, because we're not changing the tonicity of the either compartment, but we are actually getting we're actually hypervolemic. We're adding extra volume and only volume to the system.
Beautiful, beautiful. Thank you. And he explained it really well, Jonathan. I hope you got it. So we can't say that if you add just pure water here, you didn't add the solute, right? So if you didn't add solute, you're going to bring the osmolarity down in the ECF. Remember, the first compartment that is going to get impacted, whether you went to gym and you started drinking like 2 liters of water as you came back home, you are going to bring your osmolarity down in the ECF volume right away, right? Because you didn't add solutes in there. That's why they recommend if you're doing a vigorous exercise, you need to add some minerals to that and solute to that. So to compensate for what you lost getting dehydrated there or sweating there, right? So you want to add the solute as well to make it isotonic. So here the answer would be D. As Stephen mentioned, it's infusion of isotonic saline. Someone who's getting a drip of isotonic saline, they will expand their ECF by doing that. Okay, good? Yes? All right, everyone clear about this? Or do we have questions still? All right, let's go to the next, B. What do you think this is? B. B matches to Shally. Yes.
A.
B is
It
yes. Sorry. 2 is A, ingestion of salt tablets. Now you got to tell me point by point, please.
Yeah. When you ingest the salt, it goes in the ECF, so then that makes the osmolarity go higher. And then the water would rush into the ECF since the osmolarity got higher.
Okay. All right. So one thing I'm going to do here, which to help everyone understand this process. So what Shally is mentioning, we are adding solute here, right? So if they are ingesting a lot of salt here, it's going to go sit in ECF because sodium is a cation here, right? Sodium is not that permeable, remember. Only water can shift across the membrane, right? So what's going to happen if somebody ingested, you are going to take this osmolarity up somewhere here in ECF when you are ingesting. Now, this is a final state. This is a steady state. Once the salt is coming here, the cells would start to shrink and they're going to send water to ECF. Is it making sense? Once the water is coming here, it's going to bring osmolarity down here to the stage that they have shown us. So that both ICF, the cells, since they shrunk, their osmolarity is going up as well because they sent water to the other side, right? Now, both the chambers, they are at the same osmolarity now, even though it's higher because you introduce more salt here, but osmolarity, which was really high up in ECF first when you started taking that salt, but eventually when cells shrunk, they're going to come back down to same osmolarity levels. Is it making sense to everyone? Did you all get it? Yes. Zainab, you have question? Yes, go ahead, please.
So if I drink salt water, the
Yes.
volume and the osmolarity will both increase. So it'll be completely out of the box.
Yes. I mean, you are making hypervolemic. Yes. And then you are also, now it depends. How much salt did you introduce to your body? Okay. But eventually, just remember that body has to come, both the compartments, they have to come at same steady state, same osmolarity, right? How much salt has been introduced and how much water is there? That is the question. Okay. But if you are giving a patient hypertonic saline, basically you are trying to build ECF volume. The cells will shrink. Making sense, Zainab?
Yeah, thank you.
You're welcome. All right, let's go to the number 3. Noha has question. Yes, Noha, please go ahead.
Oh, I'm sorry. I was answering I was answering
Number
number 3.
3? Okay. All right, go ahead. What are you matching to?
Would number 3 be drinking a liter of pure water because your volume is going up and the extracellular space is becoming less tonic?
No, I'm sorry.
No.
It's not. It's your osmolarity going up. Noha. Volume is sideways. Osmolarity is upwards. Is it making sense?
Oh, sorry. Yeah,
Yeah.
other way around.
All right, we have Zara here. Oh, actually, I can take Isabella. I just want to give everyone a chance. Zara, do you mind if I give it to Isabella? Okay, all right. Isabella, go ahead.
Okay, so I think it would be E, loss of hypotonic fluid. My reasoning is that I'm thinking of like if you're sweating and you're losing more water than solute in the ECF, so then the ICF would compensate by like water would move from the ICF to the ECF, and then osmolarity would increase in both compartments, but you would have volume loss as well overall.
Beautiful. Thank you. Let's explain it one by one so everyone gets it. But Isabella has the answer right. So she's saying loss of hypotonic fluid. Let's let's learn the clinical scenario with this. So earlier one was if you gave your patient isotonic saline, right? You expanded their ECF volume. You gave your patient hypertonic saline. You are trying to bring the osmolarity up, and you are also building the ECF volume. Now, this condition, anyone can answer, what do you think this condition can be? She said loss of hypotonic fluid. That's like, I'm asking in a regular daily routine. How do you think it looks like? Yes, Masia?
So this would just be somebody sweating for number 3 because they're losing volume, but they're retaining their sodium. So like Miss Isabel said, you lose volume, so the square contracts, but you have the sodium. So technically it just still, there's more sodium still in the cell because you're liquid left.
Yes, thank you. Thank you, Masia. So if you are exercising, you're sweating, right? Or you are dehydrated. So you lost more solute, right? You lost more solute. Sorry, you lost more water than solute. Of course, the sweat will have some salt in it, but you are losing more water, right? So if you are losing more water, then you are obviously becoming hypovolemic here. But since the salt which was left over here, it's gonna make your cells shrink and send some water to this side, right? It's trying to compensate for that osmolarity. So cells are shrinking as well, right? Eventually, you are in a state where you are dehydrated, you lost water, maybe some solute, but your ECF was really impacted by the water loss. And ICF is trying to compensate for that condition. And that's when you're going to see the volume contraction, but in a hypertonic state. Is that clear to everyone? Are we good? Hypotonic means you lost less solute, more water. That's what it's trying to tell you. Yeah, and this will be dehydrated state. Okay, let's go to number 4. We have only 2-3 minutes left, so let's try. Zaid has a question. Okay, we have volunteers for this. Yeah, yes, go ahead.
I think this would be B.
Number 4 is gonna be B. Very nice. So you are trying to just drink like 3-4 liters of water as you came back from gym, no solute in it, right? So what will you do? You're gonna bring, if there is no solute, remember, first chamber to get impacted is gonna be your ECF, right? So you're just adding water, you are making it hypervolemic, your osmolarity is gonna come down because no solute is there. And now since this osmolarity is down and this is high, it will try to send water to the cells to bring it to the same osmolarity. So cells will expand as well. And remember, you see this dotted line little bit more expanded on ICF side. What is that? Why this one is smaller and this one is higher? Why? Can you recall something from yesterday? Anyone? Yes, Marcus, go ahead.
The ICF is going to hold more fluid than the ECF, so it's going to have 2/3 of the water content, and the ECF will have about 1/3.
Beautiful. So always remember your cells will retain more water, even though if you are infusing water into the body, that's what it looks like. Okay. Homework for tonight would be clinical condition joining to this. And we're going to revisit it next week again before the exam. So you are all ready by that time. Okay. All right. Next, number 5. Let's finish it quickly before we go. Number 5. Amelia, yes, go ahead.
C, volume and salt depletion.
Volume and salt depletion. Very nice. So can you explain us? What do you mean by that?
Sure. So the overall In 5, the overall osmolarity is decreasing, which is represented by the volume depletion. And then because there's salt depletion, water wants to flow to where there's more salt, which would be in the ICF, which is why the ICF is getting bigger, ECF is getting smaller.
Yes, thank you, Amelia. Let me answer Marcus' question. We don't have a supplemental at 1 p.m. I'm sorry, I think I was telling you yesterday, Dr. Shah likes to do his supplementals at 1 p.m. and that's why Megan was confused and I do at 8 a.m. So she was confused. We don't have any supplemental at 1 p.m. today, okay? Yeah, we only have this 1 hour of time, but I mean, if needed in future, we may use the time if available. Okay, we'll try to make use before the exams. For today, you just received this recording, and there are previous recordings as well. So please go over those. So what Amelia was mentioning here, we have salt depletion, right, and volume depletion. So ECF is getting contracted as well as osmolarity is going down. Now, when osmolarity is going down, ICF was up here to the solid line, right? So it will start shifting water towards the ICF side to bring the osmolarity down in a steady state. And that's how the cells are getting the swelling, but they will both in hypoosmolaric state since they have the solute loss and the water loss, right? And you got to draw them in transition phases. Once you get the question, just draw it out. Otherwise, you may do it wrong. Don't memorize the things for the exam, please. Okay, and if you have any questions, just let me know. All right, last one, number 6. Number 6. No volunteer? Yes, Larry, go ahead.
It's going to be F, loss of isotonic fluid, just because the osmolarity doesn't change, but we are losing fluid, so the ECF is affected first. And
Beautiful, beautiful. Thank you. So it's just loss of isotonic fluid since you don't see any osmolarity change. So it is telling you, and what condition it would be clinically. Now you know what condition it will be clinically.
Can I answer?
Yes, go ahead.
It's the one we talked about, either diarrhea or hemorrhaging.
Very nice, very nice. Yes, it's hypovolemic. Yeah, bleeding or diarrhea or vomiting, burning, all those conditions, they will go with this where the volume loss is coming from the ECF because since the solute change is equal. Okay. Do you have supplemental at 9 a.m.? Do you have any supplemental session? Okay, then I'm gonna finish the last one before we go. All right, so what do you think G is? G will be matching to what? Yes, Andrew, go ahead.
Oh, thank you. Would this be the second one? Would be number 2?
It is number 2, but you got to explain us. Now, patient is getting isotonic saline. So what made it shift to a hypertonic state?
Oh, thank you. So yeah, so what this is basically like the infusion of the isotonic saline, but with the dextran that doesn't cross the ECF into the ICF. It's basically kind of like a pseudo hypertonic solution. So what happens is the dextran stays there. It pulls more water out of the ICF. Yeah, no, or actually it raises the osmolarity and then it pulls the water out, shifting the volume to the right and then raising the osmolarity overall.
Great, thank you. So let me explain to everyone. Yes, Messia, you have a question?
No, I was just gonna help my colleague out. Dextran normally stays in the plasma.
Yeah, so basically that's what I was going to add here. Everyone, don't confuse dextran to dextrose, okay? We call this solution as plasma expander in case of hemorrhages or condition when patient is losing volume very quickly. So dextran is high molecular weight sugars that stays in the ECF. It cannot cross to ICF. It cannot cross the membrane, basically. So when you are putting in isotonic saline, dextran would stay in here and bring the osmolarity up because it's a sugar, right? So once osmolarity is up, what will happen? ICF will shrink, or the cells will shrink and send volume up here. Don't confuse it with dextrose again. If you put dextrose in your solution here, what will happen? If you put dextrose here, what will happen? Yes, Messiah.
So dextrose can cross all of the barriers, so it can go to ICF, so it will pretty much equal out. It won't shift it won't shift your volume back to ECF. It'll
Yeah, so your need of the hour is to build the volume for the patient who's going down on blood pressure, right? So if you want to bring the volume up and blood pressure up, you basically want to build ECF volume, and that you can only do with something high osmolarity or adding dextran. As I said, this solution is considered as plasma expander quickly. So you will leave dextran here in the ECF volume, which will bring your osmolarity up, and that will bring the shift of water from the cells to the ECF. And of course, you are going up on osmolarity, but you are building a volume in the ECF compartment. Is that clear to everyone? Yes, Marvin, you have a question?
Yeah, so the rule of thumb, should it be then what's gonna cause to the ECF first, then what's gonna be the what the y-axis change, and then what the x-axis
So
effect?
rule of thumb is where your solute is
Right.
going in first. Always remember your solute is going to be into your ECF. Sodium is or glucose is going to be first in your ECF chamber. So any osmolarity change will start happening in the ECF compartment. As long as you didn't add any solute, that is the rule of thumb. So as long as you didn't add any solute or sugars in the ECF, which will change the osmolarity, you didn't change osmolarity, no changes in no water shift will happen. Okay? As soon as you brought any sodium in, any sugar in, which will bring osmolarity change in your ECF compartment, the water shift is going to start happening, because water will start from hypotonic towards the hypertonic solution. Is it clear to everyone?
Much clearer. Thank you.
Yeah. So I would say whenever you see any clinical conditions that you are seeing in the book, you must do them, draw them out, transition, like in the phases. Don't just consider, oh, okay, I'm going to memorize it. No, that's not going to work. If you see something different in exam and then you are just sitting there thinking, like, how do I do this, right? So my suggestion is always draw it out. Like I gave you the first slide here. First slide, you can see sodium is getting introduced, and that will bring osmolarity up. So what will be the water shift will look like? Yes, Messiah, you have a question?
So I want to also clear up something I said, if that's okay, because I think I confused Mr. Jacob. So dextran gets trapped within the plasma, so it's something you can give with the water to bring in fluid. But dextrose, it's a good sugar that can cross all three barriers. However, it is metabolized, so it helps trap water in all of them. So Jacob, if that's better, I'm sorry for confusing you.
Yeah, let me explain that even further. So remember SGLT transporter that we talked yesterday, right? That's your transporter to pick your sugars from the compartment and bring it in the cell, right? So moment you introduce dextrose into the compartment, it's gonna enter the cells. So basically you're gonna make cells hypertonic and your volume is going to move from ECF to ICF. You are not helping your patient. Rather, your cells will be swelling and getting hypertonic. And eventually, I mean, they will come into a steady state, but you didn't help your patient by giving dextrose in there. Temporarily you can, but eventually it's just going to get into the cells. Is that clear to everyone? There may be some students who didn't get the points, and please reach out if that's the case. We have class on Tuesday, but then I can help you out with these questions further. Okay, but try doing more and more. I think there are more supplemental questions that we have in this file that you can attempt later. Okay, all right. This is it for today, and thank you all for joining. And I'll post the file soon, and let me know if you need more help. And
Thank you.
thank you.
Thank you.
Thank you.
Thank
Thank
you.
you.
Thank you.
Thank you.
Thank you. Thanks so
Thank
much.
you.
Thank you.
Thank you.
I'm staying.